Thank you, Roland, and thank you for the invitation and the opportunity. Is the microphone on with the green button? It's okay. Good. Sounds good. Yeah, I'm going to talk about the KdV hierarchy at H-1 regularity, which is a problem which I looked at for quite some time with some progress over the years, and I gave talks about that already a while ago, maybe not so many, but some, and then it took us long to complete the preprint, and it is also more complete than what we originally planned to. So I want to explain the results and give part of the explain part of the proofs. So this is the outline. Well, there is a history which you all know. There are some observations. KdV occurred as a model. It became the interest of that increased considerably when its integrable structure became clear. And then it was one of the first equations, maybe the very first equation with commuting integrals. And that turned out to be a structure which was relevant in many other problems. And it created an incredible amount of research and interest in a number of directions ranging over most of mathematics from pure to applied. My own background and your background is in PDEs. So this is something which I, when I was a student and later, realized that there is this structure, but I was more interested, I come more from the PDE side. So let me give short comment on the elements of this integrable structure. So there are infinitely many conserved quantities. There is a linearization by inverse scattering and Birkhoff normal coordinates with famous contributions. Then there's more algebraic geometric things to it. There's an infinite dimensional symmetry cube for the Korteweg-de Vries equation, which comes together with the flows of the commuting energies. And well, there is also a lot of structure, geometric structure connected to looking at the whole hierarchy at once. Now we are from a PDE community, and the question is, what is the interest in that? All these examples of higher order equations, which are somewhat naturally, but what we see is that the Korteweg-de Vries equation and nonlinear Schrödinger is an asymptotic equation which should be relevant and is relevant in a lot of asymptotic situations. And typically, if you look at waves, which we suppose we expect to be described by Korteweg-de Vries, then there are certain aspects which are much more robust than our analysis predicts. So we see that the tsunami waves travel over thousands of kilometers, and whether the one-dimensional approximation, this asymptotic regime, is valid is sort of, that regime is very questionable, but still there's some more robustness. And I guess one can see also the talk by Daniel yesterday as an element of this robustness that for the nonlinear Schrödinger equation, that somehow this picture of the wave packets somewhat weakly interacting persists even in a setting without decay. So, but if one looks at larger timescales, then the symmetry of the problem becomes important, and then the symmetry of the higher integrals probably comes in. Now, on the PDE side, there's a lot of work done for KdV. I don't want to go through that. There are some references that's not complete. There's certainly less on the fifth order equation and a little bit of analysis on the whole hierarchy. Work by Axel Grünrock, which showed that if you insist on a perturbative approach, then the conditions on the initial data have to be quite restrictive. So then, more recently, there came ideas connecting the integrable structure and the PDE side. So the integrable structure, basically the scattering structure approach, basically entirely fails if you don't have integrable initial data and moments. So from PDE community, we are more interested in L2-based spaces, and there were some ideas to get these things together. So the first was on conserved energies and uniform bounds, and I'm not sure what I would have put it at that time, but the paper with Tristan Buckmaster was can be seen in that direction, and then independently with Daniel and Killip, Visan, and Chang was a proof that there are sort of fractional conserved energies using the integrable structure. Well, then maybe the earliest paper, which sort of is now fully on the integrable side, but proved wellposedness, was Kabbalah and Tobolov for periodic KdV. And then there came this breakthrough by Killip and Visan, who proved that KdV is wellposed in a certain sense in H-1. I don't want to elaborate on the sense in which it is wellposed. I will say a bit about that later on. So that was the first commuting vector field method in their terminology. And the second KdV equation, the fifth order equation, was then studied by Brinkmann, Killip, and Visan, which uses the second order commuting vector field method. And maybe I'll say connect a bit to that later on. And this has been very fruitful, very successful. The ideas and applied to other problems. So I listed some of them: modified KdV, TOTA, but it goes beyond that. Maybe these two are the two which are closest to the setting which. Yeah. Now, what is the main result? Well, the whole hierarchy is wellposed in H-1. And I'm not specific here about on the real line. It's not on the torus. The whole hierarchy is wellposed in H-1. So what are the first integrals? The first is the integral UDX, which is conserved, but it's not so interesting. First of all, it's not defined on an L2-based setting. Second, it's a Casimir function, so it's not relevant for the dynamics. The zeroth KdV equation is the L2, which gives the translation. The first Hamiltonian is the energy of KdV, and the second is then the energy has second derivatives, which leads to a fifth order equation. And we have the Poisson structure, the typical Poisson structure for functions on these Schwartz functions. And there's this expression with a variational derivative. So then we get the nth order KdV, the nth KdV equation. I'll explain a bit how we get to the nth Hamiltonian. I will say that. And then I list the structure. So the nth equation has an order 2n plus 1. And the nonlinearity, the leading term, I only write down some of the important terms. There's a term of the u to the power n plus 1. And there is a quadratic term, which is the n minus first derivative squared and the derivative of that. So that basically gives the structure, and you can see that here. So here you have the u squared, which is the n minus 1, n is equal to 1, so that's the square. This is the second equation, so it has the square of the first order derivative, and there are ways how you can distribute the derivatives that doesn't really matter. And then there's the u cube. So this is the structure, and as we learned from the work of Axel Grünrock, if you simply look at the structure, then you don't get far by a perturbative argument, perturbative setting, if you're beyond the first order KdV equation. Now, the KdV hierarchy is connected to the Lux operator. The Lux operator is a Schrödinger operator, and what is considered as a Schrödinger operator, which depends on time. But here on this, I want to suppress time. It's not, at this point, it's not needed. And then interest is a spectral analysis of this operator. If you look at the spectral equation, so this is a self-adjoint operator. Look at the equation LU phi is equal to c squared phi, this spectral equation. Then it has special solutions if the imaginary part of C is in the upper half plane. So then what you get is you get special solutions which you can normalize on the left. Normalize on the left by pulling out the exponential factor. And you get on the right, as x tends to plus infinity, you get another limit. And this is the inverse of the transmission coefficient, which is a holomorphic function. So it's a meromorphic function. So the inverse is holomorphic. It has zeros at the eigenvalues. And this is one of the key players in the whole thing. Now, the logarithm has an asymptotic expansion. So the logarithm of this transmission coefficient has an asymptotic expansion, and what I write here is the partial sum. So if you take this, let this go to infinity, then you get the asymptotic expansion. What I write down is the partial sum, and the partial sum is the object which is of the main interest. So it's an asymptotic series, or it's a partial sum multiplied by corresponding factors of C. So this is set in a way so that it should be related to the nth order equation. So if we want to make sense of the asymptotic series which is behind that, we have to give bounds on these partial sums. And here is sum bound. So what you get is a bound of this. Maybe I should go through that. Neglect all these factors here. The important thing is this thing here, at least for large tau on the imaginary line, is bounded by tau to the minus 2, so that it decays. And it's bounded in by UNHN plus 1. The behavior for small tau is also of interest, but I want to neglect that at this point. And this is a quite useful quantity. So it's a quite useful object. One of the things which you can prove is that we are going to be interested in equicontinuous sets, which means that the translations on the Sobolev space are uniformly continuous. So, and an equivalent characterization of that is that this partial sum, this normalized partial sum, tends to 0 as tau tends to infinity. So that gives good analytic properties. Now, let me get to the next object. This is the Miura map. That's one of the next key players. What is the Miura map? Well, in the traditional form, it's the map from W to WX plus W squared. And this is a fairly interesting map. It's related to a factorization of the Lux operator, the first order operators. So it's a simple calculation that the Lux operator is given by this factorization. And that is something which will occur over and over in the setting. But there's one immediate consequence of that. And that is, if there is this factorization, then the operator is positive semi-definite. Simply because if you do this calculation, if you look at the inner product of LU phi, comma phi, and put the operator on the left to the other side, you get the square of L2 norm squared of this thing. So the Miura map is quite interesting, but it has the drawback that it is not surjective. There's a way to partly remedy that. So suppose if you don't know that the Schrödinger operator is positive definite, maybe it becomes so if you add a constant. And then this factorization still works, and it's good to pull out this tau. So this gives then this factorization here. And that is the one we work with. So that gives this modified Miura map, which maps W to WX plus 2 tau W plus W squared. And this is a fairly interesting and intricate object, even though it's first order scalar ODE which is behind that. So the main feature is the following. If you denote by U tau the set of all potentials, so that the operator, Lux operator plus tau squared is positive definite. So for those, you can find this W. And the interesting thing is that this map, which goes from L2, W in L2, to H minus 1, U tau, that, how did I define that? Anyhow, this is an analytic diffeomorphism. So it's a global analytic diffeomorphism. Pretty nice property. And then I denote this H minus 1, 2 tau as a semi-classical version, or the semi-classical version. I look at the multiplier C squared plus 2 tau squared on the Fourier side. So this is, maybe I should write it on the blackboard. H tau is defined by, so we look at the d squared plus tau squared to the 1/2, that is the m over 2, n over 2, f. So you can bound the potential U in terms of W. That's easy. And the much harder thing, which plays a bigger role than we originally envisioned, at a point which I maybe explain, is that there's an opposite inequality, which is linear. And this is not by far not obvious, that you get something linear. And there is a factor which is related to the distance to the spectrum. If U is in U lambda, then there's this estimate which is linear in U and has the distance to the spectrum in it. Now, the inverse is also not hard to describe. If you take this left Just function, then the inverse is given by the derivative of the logarithm of the left Just function, normalized by this constant which we moved it. So it's quite easy to give an inverse, which then makes it not so hard to prove that it's a diffeomorphism, and the non-trivial part, the hard part, is the. Now, proving that involves the study of this Riccati equation, and since I think it plays an important role, I want to go briefly through the argument. First, if you look at, there's a W missing, so if you look at the linear part, there should be a W here, the linear part, then it shifts the regularity on the level of Hn tau, or the 2 tau, just by 1. So the estimate and everything is perturbative for small data, for small w, small u, so the small data is not so hard. Uniqueness is again not so hard, followed by work by Kapeler, Shubin, Tobolov, I forgot the fourth author. And the global estimate must involve the spectrum. And the key observation is, if you look at the case, if U is identically 0, then there is a solution which is given essentially by the tangents hyperbolicus. suitably normalized. And the tangent hyperbolicus goes 1 plus that from 0 to tau. Do it right? Minus 2 tau, I have the wrong side. So there are these constants, and this is something which you have to exclude, and that is what is then related to the spectrum. So if there is, so if you are in a non-trivial minus 2 tau, so if W is close to minus 2 tau, then if you look at the relation to the left Just function, you look at the left Just function truncated and see that it has some bump, and that gets close to an eigenfunction. That's how the spectrum comes in. Okay, now there's more to that function. So I told you that there's this factorization. If you look at the Lux operator, you factorize it. But this immediately gives you access to the inverse, because it's not hard to invert a linear operator. So it's not hard to invert. So it's not hard to invert a linear operator of first order. Write the solution down. You can do it once, you can do it twice. So what you get is immediately access to the Green's function. And then there's this, what I want to call good variable, which also occurs in the paper of Killip and Visan with a slightly different normalization. And then there is this differential equation between W and this good variable, which is quite explicit and again as a first order equation, which can easily studied and also inverted. Now, you can write, so if you have an evolution of the KdV equation, then that corresponds to an evolution of this good variable V, of this diagonal of the Green's function. And then there's this, you get this equation here. Different ways of writing it, and I will come back to that. So, what is the idea of Killip and Visan? I want to put it into a context which then also applies to the setting which I have. Basically, the idea of Killip and Visan, but they look a bit different because I put things a little bit different. So, it's not hard to check that this T minus 1, should be KdV there, can be expressed in terms of the W. So that's the L2 norm of W squared up to a factor 1/2. So this is somewhat interesting because the map from U to W gains you one derivative. So if you look at what that means in terms of the variational derivative of that, this gains derivatives. So we are interested in Hamiltonian equations. We want to use this as a Hamiltonian. We use it as a Hamiltonian. I don't do the calculation. Then this defines, by the Cauchy-Lipschitz theorem, an evolution in H minus for U in H minus 1 or V in H1. So you can shift things around. So the Cauchy-Lipschitz theorem gives you easily some local existence. But then, since all these quantities Poisson commute, which I think I didn't say, but that's the integrable structure, they Poisson commute, they are conserved, and then you can get a global solution to this Hamiltonian. Okay, so then it's possible to calculate the Poisson bracket between V and this Hamiltonian. So that's a question of calculation, and it gives the time derivative of V. That's the Hamiltonian formalism. And one should consider this V function as sort of good coordinate. And in these coordinates, there's the calculation that this gives this equation. So V is, so we fix tau, which gives V, but there has to be an additional spectral parameter here, lambda, which is different from tau. So there have to be now two spectral parameters. You should think of tau being fixed. You may very well consider it to be equal to 1. And lambda is something which is going to be tend to infinity. So this is then Tor1, which is not so hard because it's a translation. So that differs from T-1 by a translation. And then a calculation gives you this formula, which is quite remarkable in that it only involves V. It doesn't involve U anymore, it only involves V. But it involves V at this different spectral parameters, that's this V of I lambda and so on. But anyhow, it's a somewhat robust formula. That ways of rewriting it. So let me go through the facts. So the Hamiltonians commute. This gives the conservation. The vector field of the Hamiltonian, T-1, converges to 0 uniformly. So that's what I told you, that if you have regular enough functions, then this T1 behaves like the spectral parameter to the -2. So that decays, for regular data, it decays very fast. For not so regular data, it decays still. So this Hamiltonian, the one which is related to KdV, decays uniformly in a very fast, the vector field, the Hamiltonian vector field, in a rough function space uniformly on equicontinuous sets in the V's for the good variables in H1 corresponding to U in H-1. And then I claim that the approximate flows, I write here, form a Cauchy sequence where the solution converges to the good variable KdV. So what I write here is the evolution in the V variable by a linear, I write it linearly, but it's of course a nonlinear evolution, the solution of this Hamiltonian. Now, why is it a Cauchy sequence? Well, so if I denote the evolution by lambda, here with this index, and if I pull it back with the mu variable, then I get by the commutation that this is given by the Hamiltonian vector field, the V variable of the difference. But by this expansion, I can write this parameter squared. By this expansion, I can write it as T1 minus T1 plus T1, and that converges to 0 uniformly in H-2 as the spectral parameter tends to infinity. So that gives a Cauchy sequence. And then it only involves writing the difference of the flow down. So this part here converges to the identity. So the difference converges to 0, and that is the convergence of the approximate flow. Well, now I want to change the sort of the setting a bit. I've tried to present you the argument of Killip and Visan, which was quite crucial. They worked with this, essentially with this good variable V, with this diagonal Green's function, the inverse of the diagonal Green's function. There are some advantages of choosing still other coordinates. One should think of U, V, W as coordinates. There's an advantage of using the W variable. So what do we do there? Well, we define this T-1 Gardner as a generating function for Gardner Hamiltonians. And then I present you some of the results, which I don't want to give the calculations or the arguments. But the upshot is that if you do it in this fashion, and then you get the Gardner Hamiltonians as the asymptotic expansion and so on, then the solving KdV is equivalent, at least in a sufficiently regular functions, to solving the Gardner hierarchy, the equation of the Gardner hierarchy. I have to tell you, well, first I want to give this survey what happens for the first order equation. So here we have KdV equation, which has a scaling h-3/2. The going to W involves solving a first order equation, so there's a gain of one derivative. So here is the first Gardner equation. It has a scaling of W-1 infinity, or h-1/2. What whatever you prefer. And here you have the good variable, which has the scaling of L infinity. And then it's a calculation that, well, here I put the LS for local smoothing. So one has to put local smoothing. If you want to look at derivatives in rough spaces, one has to put in this local smoothing, which I want to do, local smoothing terms, which I want to do in more detail. But then the upshot is you can go from the V variable to W, and that you can do up to H 1/2 for V, H minus 1/2 for W. And you can go for weak with weak solutions from W to U. So in the W in L infinity L2, which corresponds to H minus 1 for KdV. You can go from weak, you get from weak solutions for W, you get weak solutions for U. And in the opposite direction, it's a bit more restricted. You have to assume a bit more to get from weak solutions to KdV to weak solutions of W for W, and you can also go up. So let me define the space for weak solutions. So I want to talk about weak solutions in L infinity with values in L2. And I want to have that they have this local smoothing terms so that the nth order derivative is in L2 locally. So I regularize it by the secant hyperbolicus sum function. So the nth order derivatives are locally in L2 in space-time uniformly, and they converge to 0 for fixed intervals. They converge to 0 as we move the sender to plus or minus infinity. So they cannot have mass, so it's not accumulated infinity. And then the equations make sense in a distributional sense. And the main theorem here looks, so the first theorem is that you can go from weak solutions to Gardner to weak solutions to KdV, and also in the opposite direction with some restriction. And the main theorem is that if for W in L2, there exists a unique weak solution to the Gardner, to the nth Gardner hierarchy. So this formulation is stronger than, it's stronger even for n equal to 1 than the corresponding formulation of Killip and Visan, because here we prove existence and uniqueness of weak solutions, not only continuous extension of a flow in more regular spaces. And it's for the whole hierarchy at once. Still, the strategy is inspired by Brinkmann, Killip, and Visan with some modifications, which partly you have seen, partly you will see them later. So the first step is PDE argument. Look at weak solutions to the Gardner equation. I'll say a bit more about that, but I want to mention the steps which we do. So prove pre-compactness of weak solutions for finite time interval and initial data in a pre-compact set. So this is what Brinkmann, Killip, and Visan did. You're going to see a change in the proof in a minute. Then prove distributional convergence in a rough space to the flow to the nth Gardner equation. Prove uniqueness of weak solutions. How do we do that? Well, I think the idea is not surprising. So what you do is you take a weak solution, try to pull it back by the corresponding approximate flow, which has better properties. But the difficulty then is to show that these things commute. Once they commute, you're in a setting which you had before. So, I mean, we know commutation of the flows for smooth data and everything which we can approximate by smooth data, but we don't know that for weak solutions. We have to. Okay. So the first observation is the equation makes sense. Our assumption, so when look at this term, that's the most important term. So the nth order derivatives, that's the nth order derivatives squared we have there, and that's exactly what is given by the local smoothing term on space-time. So the equation makes sense. Sorry, this is not the equation. So in distributional sense, sorry, this is the energy flux identity in a weak sense. So that's a PDE argument. The equation makes sense. Then you do the energy flux. Write down the energy flux equation. And now it's a PDE argument to show that this energy flux identity holds for weak solutions. PDE calculation sort of not somewhat standard, but maybe a bit unusual setting. So once you have this energy flux identity, you can test it. And if you test it by a Gaussian, then you get continuity of the map as a map to L2. If you test it by a Gaussian, then only that the size of it tends to infinity, then only what happens at plus or minus infinity becomes important. Then there you assumed that the local L2 norm converges to 0. So that gives the continuity as a map to L2. Then you can do the Cardo smoothing argument. You do the Cardo smoothing argument, you get an identity which controls things which are to the right of, there should be a minus here. I think there should be a minus. I think there should be a minus here. So the things if you move the weight to the right, then the Cardo smoothing argument gives you a gain of nth order derivatives. And what it gives is a control of what happens to the, it puts the weight which is close to 0 on the left and 1 to the right. So it gives you control of that, what happens to the right in terms of what happens to the right at an earlier initial time. And that gives you tightness to the right. Okay, now the main step also of Brinkmann, Killip, and Visan was to prove pre-compactness. So the statement here is that if you start with weak solutions with a pre-compact set of initial data, then the orbits are pre-compact in L2. So I explained that the Cardo smoothing gives tightness to the right. Now with the Miura map, you can apply the Miura map and invert it. That gives control of high, so the parameter in the Miura map is a frequency parameter. It gives uniform bound, so that gives equicontinuity. That gives the control on the spectrum. And then you still need to prove tightness to the left. So tightness to the left, you get by, I think I messed up the sign of this tau again. So you let the weight, take the weight in the opposite direction, and you move it to the left. Sorry, this is still correct. Now here's the correct sign. So you get from the Cardo smoothing estimate, you get a control of nth order derivatives in space-time slab, which you can get as small as you like. And now you take a weight which has the opposite sign, 0 at plus infinity, 1 at minus infinity, and moving to the left. So that gives you then good L2 terms and bad terms with nth order derivatives. But there you have under control here, and that gives you then tightness to the left. Things cannot move to the left fast. Left on the L2 level. The difference to Brinkmann, Killip, and Visan is that these arguments here are done on a PDE level. That's the advantage of using W compared to some sort of integral equation. Now, let's go back. We go to the difference flow. Or let's say to this approximate flow. This stated several times for the KdV function, so the corresponding thing for Gardner converges to the Hamiltonian of the Gardner. And then you can also use the expansion to do various things. What is important is to look at the quadratic term of this Gardner, this approximate Gardner, or the truncated partial sum of the Gardner, and that is the n plus first order derivative. So you gain 1 in the derivative, but you measure it in h minus 1 to lambda. What is the effect of that? The effect of that is, if you look at frequencies larger than 2 lambda, then you have the full nth order derivative. But below that, you're going to lose. Minus 2, you lose a factor 2 lambda to the minus 1. So this is good concerning the high derivatives, but not so good concerning the high frequencies, but not so good concerning low frequencies. And that's what you have to expect, because it converges. So if you multiply it by 2 lambda squared, it converges to the nth Gardner equation. Gardner-Hammer, sorry. This is in Gardner, so you have this convergence, so you have to lose somewhere, and I may have messed up some factor of lambda here. So, well, suppose you look at the nth difference equation, or approximate equation, whatsoever. So this is without this lambda squared. I think I want to call it the difference equation. So this is supposed to converge to the stationary, to 0, the vector field, at least in a suitable setting. And what we want to prove is that this flow converges to the identity in some sense. Now, that's what it should. The question is, can we make it rigorous? So then we look for Carter smoothing. And the Carter smoothing which you get is related to the quadratic term, which I had described on the previous slide. And what you get is, well, you get this decay to the right. I've centered it at 0 now. You have the secans hyperbolicus, which is a bump function, which moves to the right. There's some constant here. And then there is the n plus first order derivative, but measured in h minus 1 to lambda. And you want let 2 lambda tend to infinity. So that gives you, again, good control of the nth order derivatives, but very weak control on the. That's what you get from the quadratic term, and the main proof is the proof that this holds true also for the nonlinear part. So what you have, I think I should have subtracted here the linear part of the equation. So if you look at the nonlinear part of the Gardner term, then you can bound it by something which decays in lambda. And what is important, there's W in L2, and there is this exactly the term which we gained in the square from the local smoothing from the quadratic term of this difference Hamiltonian. Okay, so this requires doing nonlinear estimates, and I don't want to go into that. And then the question is, how do you complete the proof? Well, we do induction by n, because this approximate flow involves the Gardner flow at one lower level, so we have to do induction by n. So then the nth approximate flow is well defined. The estimates and converges for initial data in Hn as tau tends to infinity, or lambda tends, it should be lambda here, lambda tends to infinity. This convergence is uniform in pre-compact sets of initial data, hence there's a unique extension to all of L2. So this is the part, let's say, of Killip and Visan, which gives the convergence of the approximate flow. Now, in order to complete the proof, one has to look at uniqueness of weak solutions. So suppose that W is a weak solution. Then we want to pull it back by this approximate flow. There's a n-1 and there's a 2 lambda squared. But if everything commutes, then we would get this equation that ut is equal to minus this, I mess up the sign, and that we showed to converge to the identity, which then implies that we pull that to the, let's say, to U, that the approximate flow converges to the weak solution, and then the weak solution is unique. So once we have that, we are done. Oh yeah, I wanted to say a bit more about that. So this is difficult part, which I don't want to say much about, but I want to say a few things. So, well, if you look at what you have to prove here, then the one question is why should it be true? So one reason why it should be true is if you look at the proof that if you have Poisson commuting Hamiltonians, that the flows commute. How do you do that? Well, you look at the two flows. You want to show that they commute. So you write the commutator and differentiate. Then you have two time variables. You flow one with one time variable, the other one with the other one. And you differentiate with respect to one of the time variables. So that gives you some sort of commutation formula for vector fields and flows. And this is obviously then true. This is a step of proving that the flows commute. And this has a better chance to be possible to prove also in our setting, this setting here. But if you look at what that means, then if you put in a different time variable here and differentiate with respect to that, then you get operators of order 2n plus 1, which you, or n minus 1, which you then apply to a weak solution, which again satisfies an equation which has higher order derivatives. So if you look at what that implies for the equation, then it's a mess. That looks entirely hopeless. But there is a way out. There is a way out, and then how did we construct the solution to the nth order KdV equation? In the end, what we did is we used this t to the -1, this generating function. So we can express any Gardner Hamiltonian as a limit of several flows, several spectral parameters of this t-1, of this generating function. So once you realize that, it suffices to prove this commutation with the weak solution on the level of the vector fields for this generating function, for this t-1. And at that point, then one really has to work. Let me go back a bit and tell you one observation. So here, if you look at the KdV hierarchy, the KdV equation, then the flow is not well defined below h-1. h-1 is the best possible thing. It's also the quantity which occurs in the Miura map, so there's no way you can go below h-1. So what about this equation? This equation looks like, well, basically it is the defocusing modified KdV equation. And it's well posed in some sense by Griffith, Killip and Visan in HS for S larger than minus half. Reasonable to expect that this equation is well-posed. I think that could be proven in h minus a half. So the range of well-posedness depends on the system of coordinates you choose here. Think of it as different coordinates. So on the Gardner level, you can go further than you can go for KdV. So maybe KdV are not good coordinates for the KdV hierarchy. With that, I want to conclude. Thank you for the attention.